In this video, we're going to work through a hypothesis test, and then we're going to calculate the probability of type 2 error. This example is taken from the Introductory Statistics textbook by Neil A. Weiss, 10th edition. So we're looking at data on the salaries of public school classroom teachers, and we're told that the mean annual salary of public classroom teachers is $55,400. Now, this is based on data from the ranking of the states and estimates of school statistics by the National Education Association. In this example, we're going to focus on the state of Ohio. And we're going to conduct a hypothesis test in order to determine if the mean annual salary of classroom teachers in Ohio is greater than the national mean. So just to recap, the population here is the annual salaries of public classroom teachers in the state of Ohio, and the unknown here is mu, which is the mean annual salary ... and then sigma is the standard deviation of the annual salaries ... And for this problem, we're going to assume that sigma is known and equal to $6,700. Oh, and notice that in the context of the problem, they give the data in terms of thousands, but I'm just going to dispense with that and just put the actual amount. So, for example, 55.4, I'm just going to write 55,400. So we know that the population follows some distribution with a mean mu, and that's our unknown, with a standard deviation of 6,700. So we're going to perform a hypothesis test. The null hypothesis is that mu is equal to 55,400. In other words, the mean for the state of Ohio is the same as the national mean, versus the alternative that the mean for the state of Ohio is greater than the national mean. And because of the form of that alternative hypothesis, we know that this is a right-tailed test. So in order to conduct this test, we're going to need some sample data. So for the purposes of this video, I made up some numbers. So that's why I said sample data and then fake in parentheses. So let's assume we have data from 100, a random sample of 100 classroom teachers from the state of Ohio. And from that sample of size 100, we observed a sample mean of $56,120. So then by the central limit theorem, because our sample size is large enough, then the sampling distribution of X bar is normal with mean mu, and the standard error of the mean, remember that's sigma over square root of n, and that turns out to be $670. And so remember that anytime we have a normal random variable, we can normalize it and get a standard normal distribution. And therein lies the derivation of the typical test statistic random variable that's used with tests of this type. So if we take our X bar and subtract the mean, and then divide all of that by the standard error, as we see here, then that gives us what we'll call Z, and that is a standard normal random variable. And since we will later need to be able to convert between the X bar and Z, then also make note of this conversion formula. You can use one to go from X bar to Z, and then the other to go from Z to X bar. And the use of this will be tacit. All right, so for this particular realization, for our particular sample, my fake sample, that is, the test statistic value turns out to be 1.07. And so now how do we make a decision? Well, remember that in order to perform a hypothesis test, technically I should have first given a significance level. So let's say we'll go with the significance level alpha equals 0.05. So how do we use our alpha? Well, since this is a right-tailed test, let's draw a bell curve, and we'll use two horizontal lines, one for X bar and one for Z. And remember that since this is a right-tailed test, we're going to put all of alpha in that right tail. And now our objective is to figure out what is the threshold of the rejection region, because the rejection region is going to be over here. So we need to know what is the value of z, and correspondingly what is the value of x bar that determines our rejection region. And in order to do that, I would suggest, if you have a TI calculator, you can use the inverse normal function, which is accessible by clicking the second button and then vars, which has DISTR above it, which stands for distribution. So from the TI calculator, if we put in INV norm and give it the argument 0.95, then it will give us 1.645. Now, by default, that is a cumulative area, so it's the area to the left. So what I'm telling the TI calculator is that this area over here is 0.95. And now let's translate that in terms of x bar. So now this allows us to specify the rejection region. If we observe a z value that is greater than or equal to 1.645, or equivalently an x bar that is greater than or equal to $56,502.15, then our decision will be to reject the null hypothesis. And this makes sense since this is a right-tailed test, because observations over here to the far right correspond to sample means that are high enough above 55,400 that we have statistically significant evidence to support the alternative hypothesis. Now recall that we calculated the test statistics, so now that we see that our test statistic and the associated value in terms of the original data set do not fall in the rejection region, then our decision is to fail to reject the null hypothesis. So at the alpha equals 0.05 level of significance, there is insufficient evidence to indicate a statistically significant difference of annual salaries for public school classroom teachers in the state of Ohio from that of the national average. Now the book continues this example with a different exercise. So let's look at this. For part A, it asks us to explain what would be a type 1 error in this case. So remember that a type 1 error is the probability that we reject the null hypothesis even though it's true. So in the context of this problem, if the null hypothesis is true and we reject it, that means that the mean annual salaries for the state of Ohio is the same as the national average. But we rejected the null hypothesis and incorrectly concluded that the mean annual salaries for the state of Ohio is greater than 55,400. Now this can happen due to random chance. Recall here was the rejection region and the bell curve that we drew whenever we conducted the test. So remember that alpha is in fact the probability that we would make a type 1 error. So if the null hypothesis really is true and the center of this distribution really is 55,400, the same as the national average, then we could have just had a bad run of luck, so to speak. So given that the distribution of x bar is what we see here, then the probability that we would have observed an x bar that falls in this rejection region is 0.05. Now a type 2 error, that means that the null hypothesis is false and we make a mistake. So that's the probability that we fail to reject the null hypothesis given that the alternative is true. So again, with a type 2 error, the alternative hypothesis is true and we make a mistake. So we fail to reject the null even though the alternative is in fact true. Now in order to calculate a type 2 error probability, we have to know what mu actually is, but of course we don't, or else there'd be no need to conduct this test. So when we calculate a type 2 probability, we calculate the probability We calculate a probability given that mu is equal to some fixed number. For example, let's say mu is 56,000. So let's say the alternative is true and the true value mu is equal to 56,000. Then in that situation, we could calculate the probability of a type 2 error. And we will do that in a second. Now for part C, the correct decision, well, that means if the null hypothesis is true and we fail to reject it, then that's a correct decision. Or if the null hypothesis is false and we reject it, then that's a correct decision. Of course, when these hypothesis tests are conducted in real life, we have no way to know for sure that we've made the correct decision. We just make sure ahead of time that we use a hypothesis test that has as good a chance as we can have of making the correct decision. Now let's suppose that the results of carrying out the hypothesis test led to not rejecting the null hypothesis, as was the case in the example we worked. Now let's classify these conclusions by error type or as the correct decision if in fact the mean salary, or mu in this case, equals 55.4 thousand. Well, in that case, if we failed to reject the null hypothesis, then we made a correct decision. And part E, the alternative turned out to be true, and that's the case where we made a type 2 error. Now let's go back and calculate the probability of that type 2 error that we alluded to earlier. So let's assume that mu is actually equal to 56,000, so that the alternative hypothesis is actually true. And remember that in order to make a type 2 error, that means we're going to fail to reject the null hypothesis even though it is false. In particular, we're going to calculate the probability that we fail to reject the null hypothesis given that mu is equal to 56,000. Now remember that we fail to reject H naught if our little x bar does not land in the rejection region. So we're talking about the probability that x bar is not an element of the rejection region given that mu is equal to 56,000. Okay, so then that's the probability that x bar is less than $56,502.15 given that mu is equal to 56,000. So let's go back and look at the original setup we had when we conducted the hypothesis test. And then let's overlay this graph with the correct curve centered at 56,000. So we want to calculate the probability then that x bar would be less than this threshold number which delineated the rejection region. That is, we want to calculate the area of this region, the area under the actual curve and to the left. So this area represents the probability of making a type 2 error in this particular case. In other words, this probability that x bar is less than $56,502.15, given that the center, the value of mu, is really 56,000. And then to actually calculate that probability, we could do another z transformation, or we can also just enter into the calculator. If you have a TI calculator, you can just enter in directly what the mean and standard deviation are. So this probability is equal to, in terms of TI calculator commands, and again, to access that, you would click second and then the vars button, which says DISTR above it for distribution. Just make sure when you enter this in the calculator, you tell the calculator what the mean is and the standard deviation. So negative infinity in TI is essentially negative 1 E99. That's what most people, I believe, use. And then so from negative infinity until 56,502.15. And let me just emphasize where those commas are. And then also, remember, we have to tell the calculator where the mean is, which is 56,000. And then also we have to enter the standard error, which, if you recall, that was 670. And so in this case, we get 0.773 and some change. So that is the probability of making a type 2 error in this particular case. Now this other area under that curve over here that I'm shading in green, this is 1 minus 0.773 and whatever the change is. That is what we call the power of the test. So let me go back. This value here, in this particular case, the probability of making this type 2 error, we typically denote that as beta. And so what we've calculated next is the power. Let me label this correctly. The power is different and is equal to 1 minus 0.773 and whatever. And the power of a test is simply the ability that we have to reject a false null. So given that mu is actually 56,000, then with the hypothesis test we just conducted, the power that we have to reject this false null, so the power we have to land in the rejection region, is this 0.2267 whatever. And so just remember that the power of a test, the way that's related to beta, the probability of a type 2 error, is that the power is equal to 1 minus beta.